All right, so the rest of section 1.2 is going to be devoted to solving two particular types of equations, the first being the linear equation and the second being a rational equation. And it seems kind of weird that these two would be blended together because the way they look initially are drastically different, but as you'll see with the types of rational equations that we'll be solving in a little bit, they eventually morph into linear equations. So that's my guess as to why they're paired together in this section. But this section is kind of the start of a series of equations that we'll be going through in this chapter. Section 1.3 focuses on a quadratic equation, and then we get to some, I guess, special types of equations, those involving absolute values, radicals, and so on and so forth. So basically from here on out in chapter 1, it's equation, equation, equation. But at the very end, we start to fold in some inequality work. So let's start with linear equations. A linear equation will involve one or more expressions which include a variable. The variable could be x, it could be y, it could be something like p, but regardless, with these equations, there's just going to be one type of variable involved. So that's why it says here a linear equation, one variable. It's a first degree equation. So what that means is that our expressions involving the variable will only include a highest power of 1 on that variable. These expressions are typically polynomial in nature, and in some cases we do have linear equations that start out with terms that have higher powers, but eventually, if it's a linear equation, those higher powers tend to cancel out. So don't fret if you're asked to solve a linear equation but you see like x squared in it for some reason. Chances are that'll cancel out and eventually you'll get to a linear equation. So there's kind of a step-by-step process that you can take when solving a linear equation algebraically. And what we mean by that word right there is you're solving it by hand. Okay, so if instructions ask you to solve something algebraically, they want to see a written out solution where you're using the techniques of algebra instead of the graphing calculator or whatever else you might have that can solve it. So with these equations and these steps right here, some of the equations may require all these steps, some might only require a couple of them. So it really just depends on what's presented to you. So this is meant to cover all of them, all right? But like I said, you might not need to apply all the steps in solving a linear equation. The first step would be to clear parentheses. All right, and you can clear parentheses via the distribution property, but in some equations you won't have parentheses to start out with, so that would be a case where you can skip step 1. Some linear equations may have fractions, and if fractions are something you would not like to work with throughout the solving process, then there's a way to clear the denominator of each fraction so that you're working with just integers. Now that doesn't mean that your answer won't be a fraction. We still have to allow that to happen, but at least throughout the process of solving for the variable, you can avoid fractions. Number 3 is kind of alludes to that phrase where you get all the x's on one side and everything else on the other. To say collect like terms involving the variable on one side of the equation, and then constants, which are just the numbers that don't have x attached to it, those would go on the other side. Then the very last thing would be to isolate the variable, and typically this is done with division or multiplication. And that would happen once all like terms and all constants have been combined. So with that, we'll get to our first equation. it's linear, you'll notice that the highest power on x on either side is 1. And what we want to do is consider which steps we really need to take from that box up there. Number 1 says clear parentheses, and obviously we don't have those, so we can skip step 1. We also don't have any fractions in the mix, so we can skip step 2. But we do have terms involving x on opposite sides. So step 3 definitely applies, and there's a couple of ways that we could do that. We could start off by moving the constants over to one side or the variables over to one side. What would you guys like to do? So I think what I would do, if you're interested in seeing that, I think what I would do is get rid of this minus x that's on the right hand side, and we could do that by adding x to it. But whatever you do to one side of the equation, you have to do to the other. So I'm going to have to add x over on the left-hand side as well. And I'll simply add that to the 5x. So these cancel. 5x plus x is 6x. Don't forget there's that plus 6 still on the left-hand side. And on the right is negative 18. Okay, so I moved the x over, and I combined it. And now we want to consider moving the 6 over to the other side. That way we have variables on the left and everything else on the right. So we can go ahead and maybe subtract 6 since it's being added on the left. Again, whatever you do to one side, you got to do to the other. These cancel. 6x is left over. And negative 18 minus 6 is negative 24. Anybody want to offer the next step?
Divide by 6.
Yeah, got it. And I'll indicate that with a fraction bar. Okay, these simplify to 1, leaving us x. And then negative 24 over 6 is negative 4. Now, I'm kind of clouding it in prematurely. It would be nice to verify this answer of negative 4, and a couple ways that you could do that is by one, plugging it back into the original version of the equation, or we could use our graphing calculators. So I'd like to do the latter, where we'll verify this answer with our graphing calculator. Okay, so let me kind of break off the algebraic solution from the graphical solution. And I'm just going to jot down the original version of the equation again. This way it helps us with our methodology. So we have 5x plus 6 equaling negative 18 minus x. Which feature do you think this might prompt us to use over the other? The intersect feature or the zero feature? Definitely, yep. So no side is 0, so it might behoove you to use the intersect feature. Now the intersect feature requires two equations, y1, which I'll define as my left-hand side, and then y2, which is defined from my right-hand side. Get a little coordinate plane in there. And let's go to the graphing calculator. Go to y equals. Press clear. 5x plus 6. Bounce down. Now we want that 18 to be a negative 18. Don't use the big minus sign. That's for direct subtraction. If you want a number to be negative, you want to use the little minus sign at the bottom. So I'll press that. And now we're doing direct subtraction because we have to subtract x from 18, so minus x. So you probably see why I call it the little minus sign and the big minus sign. So they're a little different looking, which could be helpful. Now let's see what the standard viewing window provides us with. We'll hit zoom and select option 6. So it does sketch 2 graphs, but we're not really able to see the point of intersection clearly. You can probably get a sense, though, that it's somewhere a little bit lower in quadrant 3. So if we want to see that point of intersection, we'll have to adjust one of our window settings. Any offers as to which window setting we need to adjust to go a little bit lower in quadrant 3? I'll hit the window button. We probably want to think about going lower on the y-axis by adjusting the y-min value. So currently it's at -10, so I need a larger negative number to go further down on the y-axis. And again, this is kind of a guess and check sort of thing. If you want to increment by 5 or 10 and just kind of see if you need to do any further adjusting, more power to you. I'm going to try -20. And let's press graph. And are you guys good enough with this picture? Yeah, so we can clearly see that there's a point of intersection. So let's go ahead and do the intersect feature again. Let's press second, trace, option 5 for the intersect feature. And my blinking cursor is on the y-intercept. I'm going to have to scooch it down along this graph to get closer to the point of intersection. So I'll have to hit the left arrow button a few times. And just somewhere in the general vicinity of that point of intersection is good enough for the calculator. Now, you do get questions at the bottom of your screen for the intersect feature, but as long as you're close enough to the point of intersection, you can bypass those questions by pressing enter 3 times. It's with the 0 feature that we have to worry about answering those questions. But do I have confirmation on the order paired -4, -14? All right, cool. I'm going to go ahead and sketch it out. So the graph of y1, just a rough sketch. Graph of y2. I'll indicate the window settings as well. And then the point of intersection. So it's always the x-coordinate, which serves as our solution. And that definitely verifies our answer of x equals -4. Pretty neat, huh? Okay, it's almost time for a break. What I'm going to have you folks do is attempt to solve the equation in part B. And you can just do this one algebraically. You don't have to verify your answer graphically. We'll get another round of that with one of the problems on the next page after the break. All right, so I'm going to give you a few minutes to solve part B. And in just a few moments, I'll jump in and we can verify our answers together. Okay, see how we did. All right, I'll write down the details of my solution. That way you can check yours against mine. Now, if we take different steps, don't fret. A lot of times you can solve an equation in multiple ways. But as long as the algebra is correct and we arrive at the correct answer, there's no real big issue with that. I'm going to first distribute clear parentheses. What I did next is I subtracted 5x from each side. Careful here, that's going to give us negative 2x on the left, minus 6 equaling negative 5. Then I added 6 to each side to get negative 2x equals positive 1. And then I divided by negative 2 to get x equals negative 1/2. Confirmation on x equals negative 1/2. Is that what you guys are getting? All right, sweet. Okay, well, definitely think you guys have earned the break with all that hard work. Let's meet back up at around 10, and we'll solve a couple more linear equations and then move on to rationals. All right, so I'll see you guys in a little bit. All right, gang, welcome back. You ready to rock and roll? Here we go. Okay, two more linear equations, and we'll move on to rational. These last two have fractions involved, so I'd like to show you how you can avoid working with them throughout the solving steps. But again, that doesn't imply that you won't get fractions as answers, so just want to give you a heads up on that. So we'll just have to see what we get. So the key to avoiding fractions when you're solving equations is to get rid of the denominators. And the denominators in this first equation are 3, 2, and 3. And the way to get rid of these denominators is to multiply every term by the least common multiple. Okay, so does anybody want to offer the smallest number that both 3 and 2 divide? 6, yep. So this is sometimes referred to as the least common multiple method. And what I'm going to do is place a 6 in front of all the terms, those on the left and on the right. Just one term on the left though. And here's how I'll set it up. I'll put a 6 right next to a set of parentheses. And in these parentheses will go the original terms of the equation. On the left, that's 2/3 p, 1/2 p on the right, as well as 1/3. Now what's going to happen is that these denominators are going to reduce the 6's that I've placed in front. Case in point, this 3 will reduce the 6 to a 2. This 2 will reduce the 6 to a 3. And then this 3 will reduce the 6 to a 2 again. And usually there's some stuff left over. Items need to be multiplied and maybe some like terms. All right, so on the left, we still have 2 times 2p. Okay, that's going to give us a 4p. And on the right, we have 3 times 1 times p. That's going to give us 3p. And then minus 2 times 1, which is 2. And lo and behold, our equation no longer has fractions in it. It's not solved for, though. Anybody want to help me out with our next step, perhaps? Okay, yep. Subtract 3p from each side. That's what I would do for sure. That gives us a 1p on the left, which I'll write as p. And on the right, these cancel, and you get -2. There we go. All right, let's work on part D, which we'll do both algebraically and graphically. Okay. So just one denominator here. That denominator is 3. So if we want to cancel that out, we have to multiply everything by the LCM of 3. And I guess if you want, you can include denominators of 1 underneath the 16 and the 3x. But either way you slice it, the least common multiple will be 3. And I'm going to place a 3 in front of all of these terms. So that includes the first fraction on the left, the 16, and also the 3x that's on the right. I'll place a 3 in front of all that. So 2x plus 1 all over 3. Here's the 16, and here's the 3x. Oops. Okay, so the 3's cancel from that first expression there, leaving us behind 2x plus 1. 3 times 16 is 48, so we'll add 48. And on the right-hand side, 3 times 3x is 9x. And I'm going to have you drive it home from here, all right? Go ahead and take the next couple of moments to solve for x, and then we'll go over it.
I have a question.
Yeah, go ahead.
Why wouldn't we multiply the 3 to 2x plus 1?
Because there's just one copy of this 3, and it's canceling out with, let me go ahead and, so this 3 that's in the denominator will cancel out this one copy of 3. So are you thinking, like, are you thinking we multiply the 3 to both the top and the bottom, or just to the top?
That's what I was thinking. I don't know.
I mean, you can. There is another way to do that. You could multiply it to the 2x plus 1 and place that on top of 3 if you wanted. To distribute the 3, get 6x plus 3 all over 3. But you would maybe want to then move on to breaking that up into 2 separate fractions. And then the 3 reduces the 6 to a 2 to give 2x. And then 3 over 3 simplifies to 1. So you end up getting the same result
Okay.
as we have right here. Yep. So it's just a couple of extra steps if you decide to do it that way, but if it makes more sense to you and you're more comfortable with it, you're welcome to do it that way for sure. Yep.
Oh, okay, thanks.
No problem. All right, I'm going to start jotting down my details. All right, how does x equals 7 sound? Rock on. Any questions about the algebraic solution? Okay, well, let's go ahead and see how we can do this in the graphing calculator. And just break off the algebraic work from the graphical work. And I'm going to use the original version of the equation, so 2x plus 1 over 3 plus 16 equaling 3x. So you probably can tell that we should be using the intersect feature. No side is 0. And that requires two equations. Left-hand side will be y1, right-hand side will be y2. Now in the graphing calculator, we have to be careful. The calculator doesn't know that 2x plus 1 is the numerator of a fraction unless you put it in parentheses. So we're going to have to place that numerator in parentheses since it has two terms. We'll have our slanted fraction bar for the 3, and then just our run-of-the-mill plus 16 there. And then for y2, we'll have 3x. All right, let's get to that graphing calculator. Let's go to y equals. Clear these equations out if they're still in there. and your parentheses are above the 8 and 9 keys. All right, so we'll use the left parenthesis, 2x plus 1. We'll close it off with a right parenthesis that's right above the 9. Our slanted fraction bar, 3, and then plus 16. Let's bounce down to row 2. We'll type in 3x. And let's see what the standard viewing window supplies us with by hitting zoom and selecting option 6. I'll just press the 6 button. So you may have missed it, but it does graph y1, at least a little chunk of it. And it happens really fast, but when it plotted it, you can kind of sense that the graph is going, it's like increasing from left to right. And this one's also increasing from left to right as well. So it seems as though there might be a point of intersection somewhere a little higher in quadrant 1. So let's maybe adjust the y max value, because currently it's at 10. Let's adjust it to a value that would give us a clear picture whether or not they're intersecting each other. So we'll go to the window button. And anybody want to offer just a value of y max just to try it out? Okay, we can do 20. Let's hit graph. Okay, so there's a better picture of y1. Oh, so close, so close. We might need to go just a little bit higher. Okay, I don't think this will... Okay, let's try 25. Or 2 for 50, Mr. Allen's, right? So 25. And I usually don't like a ton of tick marks on the axes. I guess it's a little bit of my OCD there. I'm going to do the Y scale at 5. You don't have to, but if you want to, go for it. Hit graph. Okay, there's Y1 again. I'm good enough with this if you guys are. I can definitely see there's a point of intersection. All right, why don't you guys go ahead and use the intersect feature to figure out where this point is at. And it should have an x-coordinate of 7, so go ahead and see if you can confirm that value. I'll check in with you in just a moment. Okay, so second trace, option 5. Scroll over a little bit closer to that point of intersection, and with the intersect feature, you just press enter 3 times once you're close. And do I get confirmation on 7, 21 as the ordered pair for that point? Okay. All right. Let me go ahead and sketch this all out and indicate the window settings and everything. So Y1 did a little something like that. We have Y2. Good call on the 25, by the way. Definitely helped out. Got 7, 21. And again, it's always the x-coordinate that serves as our solution. So according to the graphing calculator, x equals 7 was good. right, any questions about linear equations?
Yeah, I got a real quick one.
Yeah.
When you're labeling y1 and y2, how do you know which line on your calculator is y1 and y2?
The graph that is plotted first is y1.
Okay, so I got to watch it do its work.
Yeah.
All right, thank you.
Yep, that would be my advice. No problem. All right, rational equations. I hope you guys are sitting down for this because it is like the most earth-shattering fact about what a rational equation is. A rational equation is an equation that has a rational expression in it. Wow, right? I feel like Captain Obvious when I have definitions like this that I present, but that's basically it. So anytime you have an equation where you've got a fraction and some variables above and below, you know, primarily below the fraction bar, then you're in the business of rational equations. And there's really a three-step process that you can take in order to solve these rational equations, and it involves the least common multiple again, and that'll be the least common multiple of the denominators. And basically how we were solving the last two equations is the way that we'll solve these rational equations, although I will show you kind of a quicker way to solve example part A. But just to review the process, you find the LCM of the denominators. Then what you do is you clear all denominators. This is done by distributing the LCM to each term in the equation, and then we solve from there. So our first rational equation has x over x plus 2 on the left and 3 over 2 on the right. Before we get going with the solving process, I do want to take a second to just focus on x plus 2. By virtue of that algebraic expression there's a value of x that we shouldn't plug in to x over x plus 2. Anybody have an idea as to what value of x might cause trouble for us with that expression? -2, exactly. So I do want to make a note of that. And the reason for it, even though it seems a little arbitrary, is because with some equations, you'll perform all steps just fine. You'll get an answer for x. Then you check the back of the textbook, or my math lab indicates that your answer is wrong, and you find out that the equation really has no solution. But you're like, wait a minute, I did everything correctly, and I got an answer of x equals blah blah blah. If that's the case, then it probably has to do with the domain of one of the rational expressions. So what I mean by that is, if we solve this and we get an answer of x equals -2, by already noting that x cannot equal -2 in this equation, we would have to conclude that there's no solution. All right, but that's only if we get an answer of x equals -2. If we get something different for x, then we really don't have to worry about that. Okay. Now, speaking of x plus 2, I'm going to compare it to the denominator of 2. And what I'd like to do is have us figure out the least common multiple of the expression x plus 2 and the number 2. Now, when you're solving rational equations, it's a little easier to come up with the LCM versus when you have to add or subtract rational expressions, because what you're looking to do in both these fractions is cancel out the denominator. So if I want to cancel out x plus 2, my LCM is going to need x plus 2. If I want to cancel out this 2, that's the denominator of 3/2, I'm going to need a 2 as part of my LCM. So I'm going to put that in front of x plus 2. So by meshing the denominator of 2 and the denominator of x plus 2, we get an LCM that will cancel out both denominators. Now, what do you do with the LCM? Well, you're going to place the LCM in front of each term of the equation. And there's just one term on both sides. So basically 2 times x plus 2 will go in front of the fraction on the left and also the fraction on the right. And I'm going to put x over x plus 2 in parentheses, just because there's a lot of brackets, because there's a lot of parentheses already being used. On the right, 2 times x plus 2, 3 over 2. Now on the left-hand side, the denominator of x plus 2 cancels out the factor of x plus 2 in the LCM. But we're still left over with 2, which is being multiplied to x. So the left-hand side simplifies to 2x. On the right-hand side, the 2's cancel, and you're left over with x plus 2 times 3, which I'm going to write that as 3 times x plus 2. And we can distribute from here. And I'll subtract 3x from each side. That gives us negative x equals 6. Divide each side by negative 1. X equals negative 6. That look good to you guys? Now, notice that once we distributed the LCM and simplified, what started out as a rational equation turned into a linear equation. Okay. So with this section, that's to be expected. But as we learn about more and more equations, maybe after distributing the LCM, we might get like a quadratic equation or something like that. All right, but the overall process of clearing out these denominators is the same across the board. All right. Now I mentioned I would show you a different way of solving part A, and this is a different algebraic way of doing it. So let me go ahead and separate the work from our first algebraic solution and our next algebraic solution. So we had x over x plus 2 on the left and 3 over 2 on the right. So this method is based on a fact regarding fractions, namely if two fractions are equal to each other. Let's say a over b is equal to c over d. Then this implies the following. And I'm going to come up with these expressions by doing what's called cross multiplication. Anytime you have a fraction equal to a fraction, you're allowed to take the denominator of the first fraction and multiply it to the numerator of the second fraction. That would give us BC. We can do a similar thing with the denominator of the fraction on the right and the numerator of the fraction on the left, which I'm going to write as AD. If if A over B is equal to C over D, then that means that B times C is equal to A times D. And so this is often referred to as cross multiplication. And it's a technique that you could apply to rational equations, provided it's a single fraction on the left and a single fraction on the right, which is definitely what we have. So let me show you how this works with this particular rational equation. We're going to take the denominator of x plus 2 and cross multiply it to the 3. And I'm going to write that as 3 times quantity x plus 2. We'll take the denominator of 2 and multiply it to the x to give us 2x. Okay, linear equation again. We'll distribute to get 3x plus 6 equals 2x. Subtract 2x. We have x plus 6 equaling 0. And just Amazon prime that over to the right. We get x equals negative 6 again. Pretty neat, huh? Now just bear in mind that that will only work if you have a fraction equaling a fraction. So when we get to something like example part B, that's not necessarily the case anymore. We have a little bit more on the left-hand side. You know, we have 4 over y, which is a rational expression, but from that we're subtracting 5. On the right-hand side, a single fraction, but you know, it's not just a single fraction equaling a single fraction. So what we'll do is just apply the LCM, okay, once we find it, and we'll go from there. Now, the LCM is going to be based on these denominators, y and 2y. So can anybody think of an expression that would cancel both of those out at the same time?
Would it be 2y?
You got it. Yep. You definitely need 2 in there because of the 2 that's in front of y in the denominator on the right. So yep, I would agree. LCM is 2y. Very good. And we'll place a copy of 2y in front of all the terms. Okay, why don't you guys go ahead and simplify all the terms here and see if you can solve for y. All right, I'm going to jot down my steps. All right, so at some point maybe we got 8 minus 10y equals 5. Okay, what do we do from here?
Subtract 8.
Yeah, that's what I would do for sure. So negative 10 y equals negative 3, and then divide each side by negative 10. We get positive 3/10 for our value for y. Now just a quick note about the domain of these rational expressions. So looking at the of y and the denominator of 2y, there is a value of y that should not be plugged into either of these fractions, and that would be the number 0. Okay, if we plug 0 in for either of these denominators, we get division by 0. All right, so I just want to make a little note about that. Okay, and I think that's really not an issue for us in terms of our answer because we got 3/10. Now I'm going to show you how to verify these answers on the graphing calculator with a couple of these rational equations But first, I'd like to maybe keep the algebra train rolling with solving part C algebraically. All right, so let's move on to the last example for this section. Here we have a beefed up rational equation, definitely not one you'd want to meet in the dark alley, right? We got x's in all denominators, and one of these denominators includes a quadratic trinomial. And actually, that's kind of the key here. This expression, x squared plus 3x minus 10, in order to find the LCM, you're going to want this factored. Okay, and having it factored is a good thing because it helps you to see whether or not you need to include any additional factors in your LCM. So for example, in our LCM, or for our LCM, we'll definitely need a factor of x minus 2 to cancel out the x minus 2. And as you'll see, we'll also need the factor of x plus 5 to cancel out that denominator. By factoring this, we're going to see if we need anything else. Okay, so I'll just make a little note of that. We'll factor that. And let me just jot down the other parts of the equation. And to factor x squared plus 3x minus 10, you'd be looking for factors of negative 10 that add up to positive 3. And those two numbers would be positive 5 and negative 2. So the denominator factors as x plus 5 times x minus 2. So let's discuss this LCM. Okay, as mentioned earlier, we will need x minus 2 in there to cancel out the first fraction's denominator. We'll also need a factor of x plus 5 to cancel out that fraction's denominator. Do we need anything more based on our last denominator? Correct, yep. It turns out that our version of the LCM at the current moment would cancel everything out in that last denominator. So there's really no need to add anything else to this. Let's now move on to place this expression in front of all three fractions. So I'll put each fraction in brackets because it's about to get cray with parentheses. All right. Let's fill these brackets out. And we'll go ahead and simplify. We'll see how these denominators cancel, and we'll figure out if there's anything left over and take it from there. So let's start on the left-hand side. This denominator of x minus 2 will cancel out the factor of x minus 2 in the LCM. But you're still left over with x plus 5, which is being multiplied to 4. And for that reason, I'm going to write it as 4 times x plus 5. On the right-hand side, our denominator of x plus 5 cancels out the factor of x plus 5 in the LCM. But you're left over with x minus 2 times negative 3, which I'll write as negative 3 times x minus 2. Plus what? Seven. Yep. So the x plus 5 cancels out, and also the x minus 2. You're left over with 7. All right, we're back to linear equation territory. It's got some parentheses. Let's go ahead and clear those out via distribution. That's 4x plus 20 on the left, negative 3x, double negative here, plus 6, plus 7. Combine the 6 and the 7 to get 13. And if it were me, I'd add 3x to each side after doing that. Get 7x plus 20 equals 13. We'll subtract 20 from each side. 7x equals negative 7. Upon dividing each side by 7, we should get x equals negative 1. How's that look to you guys? Excellent. So let's just be sure that this is a plausible answer for x. Looking back at the factored of all denominators here, well, there was no factoring that we did with x minus 2 nor x plus 5, but this is the factored form of our last fractions denominator. There are actually a couple values of x that we would avoid plugging into these fractions. Anybody want to offer one value of x that shouldn't be plugged in to a couple of these fractions? Negative 5, yep. One more. Positive 2, got it. Okay, neither of those numbers are what we got for our answer. So no worries on that front. And what I'd like to do next is just verify a couple of these answers using the graphing calculator. As kind of a warm-up to the second equation that we'll do in the graphing calculator, I'd like to have us solve this equation using the graphing calculator. See if I can find some space for that down here. Let's kind of break it off. So let me rewrite the equation. X over x plus 2 equals 3/2. Now, this would prompt us to probably use the intersect feature. But I'll let you know, when it comes to rational equations, these rational expressions that are in them tend to give you graphs that are disconnected and have some different pieces to them. So it can get really busy looking if we graph, you know, two or more of these rational expressions and try to use the intersect feature. A lot of times you kind of can't see it because of how busy the rest of the picture is. So with these rational equations, I've found over the years that, you know, regardless of what's on either side, using the zero feature tends to be a little easier in the sense that it's easier to see the x-intercept as opposed to points of intersection when you have like a whole bunch of different pieces going every which way. So even though it doesn't look like we can do the zero feature with this equation, we actually can by moving one of these fractions over to the other side beforehand. And the easiest fraction to probably move over is the 3/2. Let's move that over to the left so that we have x over x plus 2 minus 3/2 equaling 0. And now with the way the equation is written, there's a 0 on one side. We can use the zero feature. Now in the calculator, this will be our expression for y1, but kind of like the last example of the linear equations, namely with this x plus 2 that's in the denominator, the calculator needs to know that both those terms are part of the denominator, so we're going to have to use parentheses around it when we type it in, and then the rest. Okay, so let's go to our graphing calculators. Let's go to y equals, clear out both equations. And in y1, let's type in x, fraction bar. Really important to include the parentheses. All right, let's close them off. And it's minus 3 over 2. Let's see what the standard viewing window provides us with. Let's zoom, select option 6. So if you have a TI-84, you should be seeing two different pieces of the graph, and you'll notice that they're disconnected. If you have a TI-83, your picture probably looks a little bit different. It might look like one of those cardiographs, or like you would see on like a heart monitor. Does anybody have a TI-83? Okay, so can you confirm that, can you confirm that the picture is a little bit different than what we have here? Is it kind of jagged a little bit? Yeah, so that's kind of the downside of the 83. They didn't have it figured out by then, but once the 84 came out, they were able to figure out how to get these things to really look disconnected. Now, technically, and we'll learn about this later on, but technically these two pieces are disconnected from each other. But for some reason, with the 83 calculators, the calculator is trying its best to connect the two pieces, even though they shouldn't be. But for my folks that have an 83, are you still able to kind of get an idea that there's an x-intercept over in this area? Like, is that okay? All right. So since we're using the 0 feature, we do want the calculator to help us find this x-intercept, which is somewhere over here. So let's press second trace. We'll select option 2. Now I'm on the y-intercept again with my blinking cursor. We want to be to the left of where the graph is crossing the x-axis. So there's this little blip of the graph that appears to be just under the x-axis. I'm going to try to get the blinking cursor over there. And eventually the blinking cursor does jump onto that piece. And I'm going to scooch it under to that little blip. That would be a suitable left bound. Okay. Now for a right bound, maybe somewhere on this area of the graph. That's to the right of the x-intercept. You'll have to hit the right arrow key about 1,000,000 times. So if anybody's going to be doing some gaming later, here's your warm-up for your fingers. All right, I'll press enter. And we'll just, kind of take a little shot in the dark and maybe place it right there. And that's probably good enough for the calculator, to be honest with you. Let's go ahead and press enter. And are we getting -6, 0? All right. I'm going to go ahead and sketch this out. So that little blip, and then boom. Here's where we placed our left bound. About right here for our right bound. And then the x-intercept of -6, 0. All right, x-coordinate is our solution, which is exactly what we got with the algebra version of our answer. All right. Let's see if we can squeeze this one in. So and I'm going to try to save us some writing here. This would be another format of an equation that might prompt you to use the intersect feature. But my words of advice on rewriting it so you can use the zero feature would still apply here, even though Y1 is going to look a little more involved than it did with the example part A. It's still a little easier to use the zero feature, even with this more complicated looking rational equation. So what I'm going to do is provide you the expression that you'll want to enter into Y1. It's going to be 4 over quantity x plus 2, I'm sorry, minus 2, plus 3 over, this comes from adding the negative 3 over x plus 5 over to the left-hand side of the equation. And this next fraction comes from subtracting negative 7 over x squared plus 3x minus 10 over to the left-hand side. And you'll notice that I'm using the standard form version of the denominator. I prefer to do that when typing things into the calculator, because if we use the factored version, the amount of parentheses can make it look confusing. So I'm going to have you folks go ahead and type this into your graphing calculator. You'll get and then press zoom 6 and see if you can verify the answer of x equals negative 1. Make sure you use a big minus sign when subtracting 7 over. Okay, I have everything typed in. Hopefully you do too. We'll do zoom option 6. You guys seeing this on your screen? If you have an 84, for my 83 folk, probably a little more jaggedy this time. All right. So it's pretty clear where the x-intercept might be at. Okay, it's on this middle piece of the graph. So go ahead and use the zero feature, second trace option 2. And I got to scooch my blinking cursor to an area that's a little bit above the x-axis to the left of the x-intercept, left bound. And then we have to go a little under the x-axis for a right bound. Somewhere right there is probably good. Move it close to the x-intercept. And we should be getting negative 1 comma 0. Okay, you guys getting the same thing? Rock on, you guys are awesome. All right, let me just sketch this out. Three pieces to that. Here's our left bound, right bound somewhere right here, and our x-intercept of negative 1 comma 0. Again, the x-coordinate is our solution, and that actually verifies our algebra version of the answer. All right, any questions about what we did today?